On this worksheet, we are going to be solving an electrolysis problem where we are working with an aqueous salt solution. We're going to start with an aqueous sodium chloride solution. And in this problem, we're going to calculate the voltage necessary for the electrolysis, and we're also going to calculate or determine the products that are made during the electrolysis process. So in this, whenever you're doing an aqueous electrolysis problem, you're going to start by identifying all of the different components of the solution. That's going to include the cation and the anion of the ionic compound, as well as water, because this is being done in an aqueous solution. And you also do want to consider the possibility of H plus and OH minus in the solution. The H plus and OH minus are formed by the autoionization of water, so we do want to kind of keep in mind that those are present. Once we've identified all the components of the solution, we're going to next identify all of the possible reduction and all the possible oxidation reactions. To do this, we're going to be consulting a table of half reactions. These are all written as reductions. This is just our table of potentials. And what we're doing is looking for half reactions that have all of the reactants in this particular list right here. So we're looking for any half reaction that is possible given the limitations of these 5 particular substances. For example, take a look at this half reaction right here, the Cl2 reaction. This is not a possible reaction. Even though we do have chloride, we do not have the Cl2 molecule. So this reaction could not take place. We're looking for ones that can take place. If we, let's see, if we scroll down a little further, let's see, here's one that we have, this one right here, the H plus reaction. We have H plus in solution, which means that this is a possible reduction reaction that could occur given the chemicals that we have in our solution. I'm going to copy this down. I'm going to leave the states off just to kind of save space. And also while I'm doing this, while I'm going through this process, I'm also going to copy the voltage down for each one of these half reactions. This is the standard hydrogen electrode. This is the one that has a voltage of 0. So we have a hint here that there are 3 possible reduction reactions. We found one. We're going to look for the other 2. This one right here, next on the list, this is another one that we have as a potential reaction. We have water, H2O, so this is another reaction that could occur. And let's copy that down. 2H2O plus 2 electrons makes H2, and I'm going to scroll over, 2OH minus, and let's get the voltage of this one, negative 0.8277. Now we've got one more that we need to find. And again, what I'm doing here is just looking through all of these half reactions, looking for one, here's our last one, that has all of the reactants in the reaction are things that are on this list right here. So we have Na plus an electron makes Na solid, and we want to get the voltage for this. It is negative 2.71. Now again, what we've done here is come up with a list of all of the possible reductions. Only one of these reactions actually occurs. What we're going to do next, even though we're going to skip over this problem number 3, the next thing that we're going to do is pick which one of these 3 possible reduction reactions actually occurs. To do this, we're going to begin by analyzing the likelihood of each one of these reactions taking place, focusing on the actual chemicals that are reactants. In this particular solution, we have a lot of sodium, so that's definitely reasonable, and we also have a lot of water. That's reasonable. We have a very small amount of H+. The only source of H+ is the dissociation, the automatic dissociation of water, and that occurs at a really small amount. So the amount of H+ relative to the amount of water, or Na, it's really small. And because of that, we're going to just eliminate it from consideration. We're not always going to want to automatically eliminate H+. We're only going to want to eliminate H+ if its only source is coming from water and there is no other good reactions for us to consider. So once we've eliminated an unlikely reaction, the H+ reaction, we've narrowed it down to 2 possible reactions. The next thing that we're going to do is select the one that is the thermodynamically easiest. That means the one that has a voltage closest to 0. Could be a positive number, could be a negative number. We just want something that is as close to 0 as possible. So looking at these 2 numbers, this one right here is the one that is closest to zero, this reaction right here. And that is the most likely, the most reasonable reduction reaction. So I'm going to copy it down here. 2H2O plus 2 electrons makes H2 plus 2 OH minus, and I'm also going to copy the voltage. Now we're just going to repeat that same process looking at oxidation reactions. We're going to go back up to, I'll just leave this here for a second, we're going to go back up to our list of possible chemicals, and we're going to consult the table of half reactions again. We're going to look for possible oxidation reactions. Now remember, this table lists everything as reductions. Oxidation reactions are reversed. They're the opposite. So now we're going to be focusing on the right-hand side of these equations, the right-hand side of the arrow, looking for reactions that on the right-hand side of the arrow, the only things that we see are one of these 5 substances or any combination of them. The first one that I notice is this one right here that has Cl minus. We have that. So this is a possible oxidation reaction for us, and we want to write that reaction down here, but we want to write it as an oxidation, meaning that we're going to write it in reverse. So this is the reaction that we're writing, 2Cl minus, and the products, if it's an oxidation, the products are going to be Cl2 and 2 electrons, and let's get the voltage. The voltage for this is 1.35827, and this hint is telling us that there are 4, so we've found 1, we've got to go find 3 more. Again, we're focusing on the products because we're looking at oxidation reactions. There's some OH minus. What else is in this equation? This has got H2, this equation right here, has got H2 and OH minus. We don't have any H2 that we're starting with, so that's not possible. But the next one on the list, the only thing that's over here on the right-hand side is water. We definitely have that. So here's a possible oxidation, 2H2O liquid. And the products of this oxidation will be H2O2, hydrogen peroxide, and 2H plus and 2 electrons. And then we're going to get that voltage. We're going to be using these voltages later, so it's just handy to copy them now while we're already on the table. We have found 2 of the 4. We need to go look for 2 more. So let's keep going down the list. And this is one of the times where I like using the table that's in alphabetical order, because I know that I can skip through a lot of them. Here's another one that uses water. On the right-hand side, all we have is water, so that's another potential oxidation reaction. The products of this will be O2, 4H plus, and 4 electrons. And our voltage for that is 1.229. And we have just 1 more to go. Looks like this next one underneath it, OH minus. 4 OH minus. And as an oxidation, the products will be O2, 2H2O, and 4 electrons. And this voltage will be 0.401. So now that we've identified all of the possible oxidation reactions, again, we want to select the most reasonable of these 4 because only one of them will take place. We're going to eliminate the OH minus reaction for the same reason that we eliminated the H plus reaction up above. There's just not very much OH minus relative to the amount of water or Cl minus. Once we have narrowed down to 3, we're going to select of those 3 the one that has the voltage closest to 0. That's this reaction right here. That is our most reasonable oxidation reaction, and I'm going to copy that in this space right here. Now we have identified the oxidation reaction, half reaction, we've identified the reduction half reaction. All that we have left to do is calculate the voltage and figure out the overall reaction and the products of this reaction. We're going to be doing that on the next page. Now, what we're doing next is pretty similar to what we do. Actually, it's exactly the same as what we do when we are balancing redox reactions and combining the half reactions together at the very end of the balancing process. So I'm just taking these two reactions and I'm using my technology to copy and paste them. And like I said, we just want to combine these two reactions, these two half reactions together. We know that in order to combine these together, we need to have the same number of electrons in both of the half reactions. Since we only have 2 electrons in the first half reaction, that means we need to multiply the stoichiometric coefficients of this reaction by 2. Multiply all of the stoichiometric coefficients by 2, and that way we can combine these two half reactions and the electrons will cancel. So now what I'm going to do is write all of the reactants for both of the half reactions. We have 4 H2O, we have 4 electrons, and we have 2 H2O. Let's just right now combine those together. We have 4 waters and we also have 2 waters. Let's just put that together as 6 waters. And then over on our products side, these are all of our products right here. We have 2 H2, we have 4 OH minus, we have O2, we have 4 H plus, and we have 4 electrons. Now, just like with bouncing redox reactions, we do want to be able to cancel those electrons out, so let's cross those out. Also, like balancing a redox reaction, if we have OH minus and H plus, we're going to want to rewrite that as water. So I'm going to cross off the 4OH and the 4H plus. That's going to be 4H2O. And just like balancing redox reactions, when we do this process and we rewrite as H2O, we always want to look and see if we can cancel some of those waters out. We have 4 water molecules that can be canceled from both sides. I'm going to take 4 water molecules away from each. This is going to give me an overall reaction of 2H2O makes 2H plus and O2. So these are the products of this electrolysis reaction. That's one of the answers to this question. The other thing, the last thing that we have to do here is to calculate E cell. We're going to do this the same way that we would calculate E cell for a galvanic cell. We're going to go cathode minus the anode. And remember that red cat tells us that the cathode is the reduction reaction. So let's go find the potential for our reduction reaction. Oxidation is loss, reduction is gain. Here's our reduction reaction, gaining electrons, and here's the voltage for that reaction, that half reaction. So we're going to copy that over. And then let's go find the voltage for our oxidation reaction that's taking place at the anode. Our oxidation voltage is right here, 0.1229. Now you might be thinking to yourself, wait a minute, this is going to end up being a negative number. I thought these are supposed to be positive numbers. For a galvanic cell, galvanic cells generate electricity. So for a galvanic cell, E cell is always a positive number. But for a voltaic cell requires energy. Excuse me. Not voltaic cell, for an electrolytic cell. Electrolytic cells always require energy. And so in an electrolytic cell, there's always going to be a negative voltage. This is telling us that we need to provide a total of 2.0567 volts for this reaction to occur. There's one more problem on this worksheet. We're going to do the same process, but with FeCl2. I'm going to actually do that as a separate video so that this video doesn't get too long.